Hey everyone! So today I'm going to be doing a lesson on kinetic energy and potential energy. Not so much about the formulas, but how you can derive them and how they relate to each other. So, starting off, let's derive the formula for kinetic energy. So first I'm going to give you the steps and then I'm going to show you how you can do it. So you guys know, and if you don't remember, go on my previous video about work and energy transferred. You know that work, by definition, is the force times the distance traveled in the direction of the force. So work equals Fs, okay? So if you want to derive the formula for kinetic energy, first get the formula for S, where S is to do with the average velocity, okay? Because you are not going to assume that your velocity is constant, okay? Then step number 2, get the formula for acceleration. So you know what acceleration is overall, okay? And again, if you don't know what I'm saying just right now, wait until my next slides. And then you know that force equals mass times acceleration. So from the acceleration, multiply by mass and get the formula for F, and then multiply F and S together. And because F times S is the work done, and work done is the energy transferred, work done should give you the kinetic energy, which is 1/2 times the mass times the velocity squared. So let's see this in action. Kinetic energy is the work done to move an object through a distance s, right? So s is going to be my average velocity times the time. Remember that velocity equals distance over time, so distance equals the velocity times the time. Now again, I want my average velocity, so I'm going to do 1/2 of my initial velocity plus my final velocity, okay? So I'm adding the two velocities together and then dividing it by 2. And then I multiply that by t. So I'm going to get that this is going to be equal to 1/2 times vt, because initially, if I'm not doing any work, I don't have any velocity. So my u, my initial velocity, is 0. So that's the explanation there. My u is 0. Now, I'm going to get the formula for acceleration. I know that acceleration, by definition, equals the final velocity minus the initial velocity divided by time. Again, I do not have an initial velocity, so this formula simplifies to v over t. Because from Newton's second law, force equals mass times acceleration, I can substitute the acceleration by v over t, so I get force equals ma, which is equal to m times v over t. So now, if I want to go and get the work done, I just need to multiply the force by the distance, right? So I do Fs, so F m times v over t times s, these guys. So 1 over 2 times v times t, 1/2, the mass, times, and I have v here and v here, so times v squared, and then I have t, and then here multiplying and here dividing, so the t's cancel out. So I just demonstrated to you that I just derived the formula that work equals kinetic energy and equals to 1/2 times the mass times the velocity squared. Now, we are going to do the same for the formula for GPE, gravitational potential energy. So again, work equals energy that is being transferred, so is the force times the distance. Now, for F, pick up the force of gravity. For S, pick up the distance that you move up and down, so this formula is easier to derive. And you should get that the work done is the change of my gravitational potential energy. It should give you this formula if you get it right, okay? So again, if you want to try, pause the video. Otherwise, here's the answer. Gravitational potential energy, that's the energy of an object due to its position. So the higher up you are, the more potential you have, the more gravitational potential you have, okay? So the force of gravity, Fg, equals the mass times the gravity, so the gravitational field strength actually, okay? And the distance moved vertically, I'm going to say delta h, h for height, and then delta because I'm going to change that height, right? So my work done equals the force times the distance moved in the direction of the force, so that's going to be my change of gravitational potential energy, because I get F, mg, times delta H, okay? So here I go. I just demonstrated as well, or derived the formula for gravitational potential energy. Remember that G is a constant. It depends on the planet where you are. So the gravitational field strength is 9.81, okay? And you could use the units of newtons per kilogram or meters per second squared, okay? Or meter second minus 2. All right, so now how do they relate? Gravitational potential energy and kinetic energy, they are the same in terms of changes. So as I change my gravitational potential energy, I actually change exactly the same amount. Did you see that? So I actually change the same amount of kinetic energy. Of course, this is considering that I have no waste energy. So this is in ideal conditions. So my kinetic energy, as it increases, for example, in this example, my potential energy decreases. But if I add the two functions together, if I add the two energies together, they always give me the same number. So the total energy of the system is always the same. This is an example. Imagine a pendulum, and my pendulum has the mass going up and down, right? Now, when I'm going on the edges, so on the maximum displacement from the equilibrium, I have no velocity, because if my velocity is 0, that's the point where my mass is going to stop going up and is going to stop and change direction and go back down again. So I have 0 kinetic energy. However, I am on my highest point, so my gravitational potential energy is maximum, okay? As I go down to the lowest point, which is the equilibrium, I now have 0 potential energy, because I would have mass times gravity times 0, so it's 0 potential energy. However, my kinetic energy is the highest because the point where I'm in lowest here, so the point of my equilibrium, is going to be the point where I have the maximum velocity, because I just dropped as much as I could and now I'm just going to go up. So if I draw the functions of this situation, this is how they look like. A and minus A are here the displacements, okay? So my kinetic energy is 0, increases up to the 0 here, which is the equilibrium position, the 0 displacement, and then decreases in the same proportional, okay? So it's the same, it's kind of symmetrical. My potential energy is doing the opposite. Is maximum at the edges, at the maximum displacement, 0 at equilibrium, and then it increases again to the maximum displacement where it gets its maximum value. So my change of gravitational potential energy equals my change of kinetic energy, okay? Now let's just do an exercise involving all these things, okay? And again, this is not mine. This exercise, the PowerPoint is mine, but the exercise is from AQA, all right? So they say there's a fairground ride, and they have a track going down by a vertical drop of 55 meters, and this is over a distance of 120 meters along the track. They give you the mass of the train, 2,500 kilograms. They say that the maximum speed is going to be 30 meters per second, which is at the bottom of the descent, of course, and they say that the initial velocity is 0 because they say is at rest at the top. They want the loss of potential energy, the gain of kinetic energy, and the average frictional force on the train during the descent. So, loss of potential energy, well, I'm going to drop 55 meters. That's my vertical drop, so that's my height difference. So it's the mass times the gravity times the drop. So 2,500 times 9.8 times 55, that gives me 1.5 times 10 to the power of 6 joules. Joules is the units for energy. Now, my gain of kinetic energy. So I use the formula for kinetic energy. 1/2 times the mass times velocity squared. So 1/2, 0.5 times the mass, 2,500 times velocity squared, 30 squared. Now, the thing is, this is going to give me 1.13 times 10 to the power of 6 joules. Now, these numbers, in theory, would be the same, right? Remember? Let me just show you here. The total energy is the same. The change of gravitational potential energy should be the same as the change of the kinetic energy. However, That would be in an ideal situation with no friction, with no air resistance, with no energy being lost to sound or heat, okay? So that's why they have question C. What is the average frictional force on the train during the descent? So I'm going to have some of the energy that is going to be lost because of friction. So how do I calculate it? Well, I know that work equals force times distance. And my work to overcome the friction, so my energy that is lost is the difference between the potential and the kinetic energy. So I do potential energy minus kinetic energy, and this gives me 2.2 times 10 to the power of 5 joules. So that is the difference in the two energies. That's my work done because of friction, okay? Now, the work done equals the force times the distance. And I know that I have a distance of 120 meters. So I rearrange the formula. Friction, or the frictional force, equals work over distance. So the number that I calculated for work, 2.2 times 10 to the power of 5, divided by the distance, 120. And this gives me 1,830 newtons. So here you go. It's really simple. Just make sure you have the formulas, you substitute the values, you give the units, and this is how you work out either kinetic energy, gravitational potential energy, or you play around with loss of energy and getting to know the frictional force, okay? So that is it for today. I hope it made sense. Otherwise, just speak to me directly. Be happy and healthy. Until my next video. Bye!